Welcome to another wonderful edition of Comet Algebra. This video is for Algebra 1, Chapter 8, Section 6, Exponential Growth and Decay. So first, a bit of review. We learned that we can write exponential equations as y equals a times b to the x, and in word problems, we're going to refer to that as y equals start times growth to the x. Now, exponential growth and decay happens when a function is increasing or decreasing by the same percent each time. So the growth rate is the percent of the increase or the percent of the decrease. In the 8.5 video, we looked at a problem that was bacteria doubling. So I don't know if you realized it, but at that time when we did that problem, when something doubles, then it is increasing by 100%. So we'll talk more about this growth rate. The rate is a percent, and the growth factor is a number, like 2. So we'll have to work on that to understand the rate and the factor. Remember, an exponential function is increasing when the growth is more than 1, like it's increasing when the growth is 2 or 3 or 4, and it's decreasing when we have a fraction that's in between 0 and 1, like 1/2 when the growth was 1/2, or if the growth is 3/4, could be 7/8, anything. So that was the difference, not positive and negative slopes like it was in linear, but a whole number bigger than 1 for increasing, and a fraction less than 1, well, in between 0 and 1 for when it's decreasing. So let's look at the notes here for exponential growth first. Y equals start times 1 plus the rate to the x power, or your book uses a capital letter A to stand for the initial amount. So that capital A is the start, and then the growth is 1 plus the rate to the t. And I wanted you to see this because we can write this with other variables besides x. In function notation, f of t equals start times growth to the t. Now let's discuss a little bit this growth rate and growth factor. The growth rate is given to us in a percent. In exponential growth, it's the percent that the function is increasing by, and we have to take that percent and turn it into a growth factor to put this into our equation. So again, the growth rate is the percent that we're given in the problem. The growth factor is something that we figure out to put into the equation. And I'd like to look at kind of a silly example here to help explain that to you. Because you could be wondering, what is the deal with this 1 here? And I want that 1 to make more sense to you. So let's look at my silly example. If there's a town that grows by 2% each year, and right now there's 500 people that live there, how many will live there in 7 years? So I'm going to do this wrong to show you why the 1 is there. So remember, this is the wrong way to do it. We may think that y equals the start, obviously, is 500 people, and the growth is 2%, and we write that as a decimal as 0.02. And then the x is the number of years that go by. Now remember, this is wrong. I'm doing this wrong to show you something. So if we punched this out in our calculator, if we put the 7 in for years, you would get a ridiculously small number of 0.00 whatever 64. And that can't be the number of people that are going to be living in this town in 7 years. So the question is, what did we do wrong? Well, by not putting the 1 here, this 1 is so important, because if I put the 1 into this problem, this 1 represents the starting population of the town in our growth. So my silly thing I say is, if you don't put the 1 in there, you have just killed off the entire town. And the 0.02 is just the growth. So the 1 becomes the representation of the population of the town in our equation. So now let's do this correctly. When it's growing, we have to take 1 plus our growth rate. And now when I enter this into the calculator, by the way, your calculator knows PEMDAS and would never multiply this first and then raise it to the 7th power. Your calc will take the 1.02, raise it to the 7th power and get an answer, and then multiply that by 500. And then we get a much more reasonable answer of 574 people. Of course, we round off to the nearest person. So once again, this 1 represents the amount that you're starting with. And you have to have that 1 in there to have the stuff you're starting with and then add on or increase it by your growth. So in this problem, the growth rate is 2% and the growth factor is 1.02. We're going to talk about those two a lot more. But first, let's talk about exponential decay now. You'll notice the notes for this are very similar, except you have a subtract sign here. In exponential decay, it's going down, so we have to take the 1, which represents the starting value, and we have to subtract whatever the growth rate is, whatever this percent is. So a quick example we could look at is if your $6,000 car, I forgot the word car, decreases by 8% per year, what will its value be after 5 years? Well, to find the value, to find the y, we have to take the start, which is the 6,000, and we have to take 1 minus the rate, because we're starting with our initial and we're losing 8% per year. 8% as a decimal is 0.08, and this x is how many years go by. So let's go ahead and subtract that. And that would give us a growth of 0.92. And that also makes sense because if you're losing 8% per year, you are keeping 92% per year. So now let's put in the 5 years for the exponent. And we get about $3,954 for the value after 5 years. So I hope this helps you understand why we have the 1s in here and why we subtract when we're in decay and why we add it when we're in growth. All right, these examples are to help you learn to identify the parts of the equation. What is the initial amount, the growth rate, the growth factor, and what type is this? Is this growth or decay? So let's look at letter A here. We have f of t equals 500 times 1 minus 0.75 to the t. So the initial amount here obviously is 500. The growth rate is 0.75, or you may want to write that as a percent, 75%. Now I'm just going to stop a minute. Because we see this subtract sign, we know that this is decreasing. And so I don't really have enough room to write the word decreasing. So I'm going to put a minus sign here to clarify that this is a decreasing problem. It's a decay problem. So I guess I just kind of answered the question here for what type is it. It's definitely decay. And what is the growth factor? What is 1 minus 0.75? And of course that is 0.25. If you're losing 75%, you're keeping 25%. So you work ahead of me now. Hit pause on the video and fill in to the best of your ability B, C, and D. And then start the video when you're done to check your answers. Okay, now take a minute. You might want to hit pause now that you can see the answers and check yours. And if you want a brief discussion here, I hope letter B is kind of obvious to you that it's increasing by a factor. The factor is 3.5, so it's increasing by 250%. C, I rewrote it here. Perhaps this can help clarify. There is no number in front of this 2, and when there isn't, we know there's a 1 there. So that's why the start is 1. And then the 2 can be split up into 1 plus 1, so that's why it's 100% growth. In other words, this is doubling. So when something is doubling, the growth factor is 2, the growth rate is 100%, it's increasing by. And then to help you understand letter D, I rewrote the growth here in the equation is 1/2, and that would be 1 minus 1/2 to show you the decay there. So if this isn't clear to you, please ask questions in class. Now let's practice writing these exponential functions in the form y equals a times b to the x, or in this case f of t equals a times b to the exponent of t. So in letter A here, the initial amount, the start, is 15. So I'm going to write f of t equals 15. And now we have to calculate the growth factor. Our growth rate is 350%, which we change to a decimal of 3.5. Since it's increasing, because this percent is growing, we know this is a growth problem, so we have to have 1 plus the 3.5 raised to the t power. And so I'll write that, I'll put that together, and have 15 times 4.5 to the t. And quite clearly, this is an exponential growth problem. Now let's look at letter B here. Let's read it. This time we have an initial amount of 80 and a growth rate of negative 45%. Another way they could have said this is that this quantity is decreasing by 45%. So again, we'll use the function notation f of t. Our start is 80. Since it's decreasing, we have to do 1 minus the 0.45, and we'll raise this to the power of t. Go ahead and subtract that in the parentheses, and our equation would then be 80 times 0.51 to the t. And of course, this is an exponential decay problem. A very useful model for using exponential growth is when we are compounding interest. A stands for the amount in your account, equals the P is the principal, meaning the money that you start with, times, and your growth factor is 1 plus your interest rate. And here I just wrote it in words, which I think can be very useful. The total amount in your account equals the money that you start with times 1 plus your interest rate raised to the exponent, which is the number of times you're compounding. You need to understand some terms here to figure out how many times you're compounding. If you're compounding, which means calculating the interest, if you're calculating the interest annually, that just means 1 time a year. Semi-annually means twice a year. Quarterly is 4 times a year. If it's calculated every month, of course, that's 12 times a year. And if it's compounded daily, that means they calculate the interest on your account every day, then that's 365 times a year. Now, the interest rate is always going to be given us in what's called APR, which stands for annual percentage rate. Except we're not always going to be compounding the interest just once a year. So we need to do some dividing here. For instance, if you're doing the compounding semi-annually, you'd have to take your APR, whatever that is, and divide it by 2, because semi-annually is twice a year. If the problem is telling us that we are compounding quarterly, we have to take that annual percentage rate and divide it by 4. If it's monthly, you divide by 12. If it's daily, you divide by 365. So let's look at this in an example. We are asked to find the account balance if $10,000 is compounded quarterly at 5% APR, and they're asking us to do this for 15 years. So let's set up the equation. A is the amount that's in the account, equals the starting money. Well, we're starting with $10,000, and we're compounding it quarterly. So before I can make the equation, I have to change this annual percentage rate into quarterly. So we take our 0.05, because we're not compounding once a year, we're cutting that year up into fourths. So we need to divide by 4. And that gives me 0.0125. So this is my quarterly rate. And this is obviously growing. We always want our money to grow in our accounts. So we're taking 1 plus that 0.0125. And now we have to raise this exponent to the number of times that we're compounding. Now, if we're going 15 years and you're compounding quarterly, that's 4 times a year, we have to take 15 times 4 and get 60. And that is the exponent. So you'll notice this 4 is used twice. You divide the interest rate down by 4 to get the quarterly interest rate, and you multiply the number of years by 4 to get how many times you're compounding. And now this becomes calculator work. And if I punch that in correctly, I got at the end of the 15 years, we would have $21,071.81 rounded off to the nearest penny. All right, let's just do example 3, which has these 4 parts, and then we should be done. So go ahead and write the equation. Hit pause on the video now, write the equation, and then come back and see if you agree with what I have written. So for letter A, since we are only compounding annually, which is once a year, we don't have to change the 6%. We just use 0.06, and we use the 30 years. And then I'm going to go ahead and put this into the calculator to see how much money I'll have after 30 years. And I got $349.12 rounded to the nearest penny. So now hit pause on the video and do section B here, and you just have to make some changes because we're compounding monthly. So you're going to have to divide the interest rate down by 12 and multiply the number of times we're compounding by 12. So when I divided this 0.06 by 12, I got 0.005, and 30 times 12 is 360. So now we have made our adjustments for compounding monthly. So now enter this into the calculator and see if it makes a difference if they're compounding only once a year for your account or if they're compounding it every month. And you can see it made a huge difference. Compounded every month, now we have over 600,000 after our 30 years. All right, let's move on to do part C and D. Again, hit pause on the video and you set up the equation for part C and then start it up and see if we agree. All right, so if you did this quarterly compounding correctly, we needed to take this 0.05 and divide by 4 to get 0.0125, and take your 4 years times 4 because we're compounding 16 times, and let's see how much money we'll have with this example. And I got $14,638.67, always rounding to the nearest penny. And remember, you are doing this amount raised to the exponent first, and then do this multiplying second. Remember your PEMDAS. All right, hit pause, set up part D, and we'll finish up this video. All right, so if you took 0.05 and you divided by the 365 days in a year, you get a very tiny number here that we're adding to the 1. And then we have to take this 4 years times 365 and get a very large exponent. All right, so let's enter this now and see how much money we end up with that same amount of money, but if they're compounding it daily instead of quarterly. And we can see we end up with just a little bit more money than compounding quarterly. So now you have the knowledge you need to do section 8.6, so have fun with math.